Hi everyone, welcome back to Dave's Math channel. Today I'm going to do another number theory video. I'm going to talk about a very important result, probably one of the most important mathematical proofs ever done, namely Andrew Wiles' proof of Fermat's last theorem. And this problem has a very long and kind of notorious history. Here's what Fermat's last theorem says. It says that if n is a positive integer greater than 2, then there's no solutions in positive integers x, y, z, such that x to the n plus y to the n equals z to the n. There are for n equals 2, is infinitely many solutions. These are called Pythagorean triples, and I'm not going to go into Pythagorean triples. These have been known since the ancient Greeks, and I even made another video about them. That's fascinating of itself, but it's kind of interesting to know that for any integer n greater than 2, there's no solutions. And there was a very famous number theorist named Pierre de Fermat, French number theorist, lived in the 17th century. And he thought he proved this. He thought he proved this result. And that's why it became known as Fermat's last theorem. And he left a very notorious remark. Here's a picture of Fermat, and this is, again, what it says. Eventually, it took like 358 years to prove this. Fermat thought he proved it. And, for over 350 years, other mathematicians tried in vain to find his proof, and none of them did. And I think he didn't prove it. I'd be extremely surprised if Fermat actually proved his theorem. He might have proved it for some special cases. As a matter of fact, I think it's known that he proved it for n equals 4. N equals 4 is pretty easy. N equals 3 isn't too bad either. You can use a method called the method of infinite descent. I'm not going to get into that, but it's not that hard to prove. I've done it. But here's what he wrote. And let's see if I can read this. He says it's impossible. The English translation says it is impossible to separate a cube into two cubes, a fourth power into two fourth powers, or in general any power higher than the second into two like powers. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. So he never wrote down his proof. He said that he found a proof and he didn't have room to write it down. But I don't think he found a proof. This baffled mathematicians, like I said, for over 350 years. There was even an episode of Star Trek The Next Generation. I think, it was kind of ironic, because I used to love that show. I watched just about every episode. I think I did watch every episode of The Next Generation. But there was one episode, I think it came out around 1989, maybe, probably about 5 years or 6 years before Andrew Wiles actually proved it. And according to this show, which was supposed to take place in the 24th century, Jean-Luc Picard said that Fermat's last theorem still hadn't been proved. So kind of sad that they thought that was going to be the case in the 24th century. It turned out it was even proved before the end of the 20th century. So very difficult to make predictions about the future. But anyway. Let's keep going. So here's the progress that was made on solving Fermat's last theorem. It wasn't proven for all exponents. That's the proof. The statement applies to every exponent n. But what was done was that it was proven for certain special values of n. It was first proven for n equals 4. That's the easiest case. That was proven by Fermat himself in 1670. N equals 3 was proven later. That turned out to be harder. But there was another very famous mathematician, another number theorist, Leonhard Euler, who proved that case a century later, 1760. And then the next case, n equals 5, was proven in 1825. You can see how slow the progress was on this. Just to get up to n equals 5, it already took, almost 2 centuries. So this was done by Dirichlet and Legendre. And n equals 7 was done by a guy named Lamé in 1839. Later, I think it was proven that you only needed to prove it for primes greater than 4. So it's enough to prove it for all primes up to a given bound, then it automatically holds for composite numbers up to that bound as well. So the bounds kept getting bigger and bigger. There was another number theorist named Kummer in 1847. He proved that it was true for all certain types of primes known as regular primes. I think he even thought that all primes were regular when he came up with his proof. So he actually thought he had a proof, but it turned out it didn't work for all primes. It only worked for these special primes called regular primes. But it turns out that every prime up to 37 is regular. So the limit for this case was 36. And then there was a guy named Vandiver. This is already in the 20th century, 1926. I don't even know what method he used, but he proved it for all numbers up to 136, 156 in 1926. And he used his method, I guess later, 1937, he improved that bound up to 606. And then 1954, the two Lamer brothers, D.H. Lamer and his brother D.W. Lamer, as well as Vandiver again. They used their method to prove it up to exponents up to 2520. I think then later, you had the computer age, and by 1993, you could use computers, I think, to use the same method that Vandiver and the Lamer brothers had used. I don't even know what method they used, but they were able to prove this for all exponents up to 2 million. And that was just a couple of years before Wiles finally proved it for all exponents. So now we do have a proof. But his proof was horribly, horribly complicated. He wrote a 129-page paper. Here's a picture of Andrew Wiles, by the way. Yeah, he was from Princeton. Yeah, not only did he prove Fermat's last theorem, he proved another very important result in number theory known as the modularity theorem. As a matter of fact, he had used part of the modularity theorem to prove Fermat's last theorem. The method he used was a very, very complicated method. It involves a math that wasn't even invented until the 20th century, involving elliptic curves and modular forms. I guess he had to prove enough of this theorem called the modularity theorem, which basically says that all elliptic curves are modular. He didn't completely prove that until 2001, but he proved enough of it in 1995 to prove Fermat's last theorem. Here's the first page of his proof. But this paper, was 129 pages long. And my thesis advisor, Hendrik Lenstra, he gave a lecture on this shortly after this proof came out. And one member of the audience asked him, he said, "How long do you think it'll take you to understand this proof?" And he gave a pretty clever answer. He said, "Well, I think I could probably understand it in about 3 years." But he said, "You have to realize that I'm 44 years old." I guess that's how old he was when he lectured on it. He said that means it's going to really have taken me 47 years, which I thought was kind of funny. But no, I mean, forget it. I'm never going to understand this proof. I don't really care. It was so hard to prove. I think there was a French mathematician in the 18th century who he was getting. I think he was also a professor, and he was getting all these bogus proofs of Fermat's last theorem. And what he did was he made a special stamp saying there's an error on your proof on page blank, line blank. And he hired a student to grade, to read all these alleged proofs, and he told his student to stamp each of these alleged proofs and fill in the blanks. Go through the proof, find what page and what line there was an error on the proof. I feel sorry for the student, but I guess they did all have errors. So there were so many wrong proofs, but finally Andrew Wiles came up with one that worked. Pretty remarkable. And it was so well publicized. This was the paper that came out of the New York Times. I think I should say one more thing about this proof. He thought he had a proof in 1994, but it turned out his first proof had a small error in it. So he had to fix the error, and that took him another year. So he didn't actually fix his proof. The actual proof wasn't even done until 1995. And I think just about now, even though it's almost impossible to go through his paper, I think the consensus among just about all mathematicians in the world is that Andrew Wiles' proof is sound. It does hold water, and he did actually prove Fermat's last theorem. So hooray for Andrew Wiles! And yeah, I mean, I don't know if he won the Fields Medal for this. Oh, he couldn't have because he was too old. I think he should have won the Fields Medal for this, despite his age. I just think it was an amazing proof, amazing result. And yeah, kudos to Andrew Wiles. And anyway, that completes my talk for today on Fermat's last theorem. Thank you for watching. Long live math, and I'll see you guys next time.